So the topic we're about to start will focus on so-called readers-writer locks, and you get to learn what they are and why they're cool. Basically, as we'll see, there's several different types of reader-writer locks. We're going to be focusing primarily on stamped locks. We may or may not cover the reentrant read-write locks. You'll see why as we go through this stuff. Before we get into the details, though, let's first talk at a high level, what is a readers-writer lock? So it's basically a synchronizer that's used to solve readers-writers problems. Okay, well, that doesn't really help much. It just kicks the can down the road. You can read more about that at Expedia. So the metaphor here is we've got a bunch of readers, and they're all doing things, in parallel. They're all reading in parallel. And we also potentially have writers that make changes. So what a readers-writer lock does is it allows concurrent read access to a shared mutable entity, shared mutable state. And the way this is going to work is we're going to have a critical section, and there can be multiple reader threads running in the critical section at any given point, accessing the contents, reading the contents. And while there's readers in the reader-writer critical section, anybody who wants to write ends up queuing, waiting for their turn to write. When it's some writer's turn to write, two things have to happen. First of all, there can't be any readers. The readers, if there are any readers at that point, they'll be queued on another queue waiting for their turn to get a chance to run. And there can only be one writer at a time. So multiple readers, but only one writer at a time. So that gives you exclusive write access, which, if you think about it, is what you want to do. This type of an abstraction is most useful when there's lots of concurrent threads that are trying to access a shared resource. So in the analogy here, we've got some shared resource like a dish full of nuts, and we've got a bunch of readers and writers, and we want to be able to have lots of threads in there reading the nuts. Why you would read nuts, I have no idea, but it gives you the abstraction. But only one thread at a time can write to it. And so when there's writing, there's just one happening. There are two types of readers-writer locks in Java. Stamped lock is the souped-up high-performance model version, and then there's the reentrant read-write lock, which is the older, slower legacy version. And we'll talk about both of them, focusing primarily on stamped locks. Reader-writer locks may help to improve performance. No guarantee, but they will sometimes help to improve performance. And the circumstances under which they improve performance is when resources are read much more often than they're written to. So if you have something that's mostly read, then it's a win. I'll give you a human known use here in a second. We've talked about one before. This is especially true on multi-core, multi-processor platforms. In fact, you could probably make the case, in fact, I would make the case, that if you don't have multiple cores and multiple processors, it's probably a complete waste of time to use a readers-writer abstraction. Because if you only have one thread, if you only have one core, then you may have 20 reading threads, but there's only going to be one running at a time. So it's probably overkill to use a readers-writer lock in that situation. There are some downsides to using readers-writer locks, however. In practice, there are some tricky issues. One problem is they can lead to what's called starvation. And there's a bunch of variants of this. The real question is, who takes preference when there are multiple readers and multiple writers? Do we give preference to readers, in which case we might starve writers? Or do we give preference to writers, in which case we starve the readers? And it turns out that Java has had different semantics over time. Another problem is if you don't implement these things properly, you can actually make them be slower than mechanisms that don't enforce a readers-writer protocol. So, just using good old synchronized statements or reentrant locks. There are use cases which readers-writer locks, especially the legacy variants, are actually slower in many cases unless you have very, very peculiar use cases and scenarios. They can also be somewhat hard to program. As you'll see, especially some of the advanced features of StampedLock take quite a bit of thinking to get right. And so you've got to really make sure you've got the right use case before you spend a lot of time doing this. So what's a human known use of a readers-writer lock? My favorite example is one I think I've used before. The Vanderbilt course catalog is something that is changed periodically, probably once a year, probably in, I don't know, April or April 3rd or whatever before the next registration round opens. And so during the rest of the time, it's a reader's paradise. You can go and read the Vanderbilt course catalog. There's lots of people reading it. Thousands could be reading it at the same time. And so in that case, you don't want to slow people down, really, if there's lots of readers. But when you're going to change it, you don't want to have people sort of get half a document. So you want to make sure that you correctly lock it when it's going to change on its annual basis. So that's basically the point of this slide. There are lots of other examples too, of course. Okay, so that's the end of the overview. That should just give you kind of a high-level perspective on what readers writer locks are. So the second part of the discussion on reader writer locks will talk about some of the key methods that are in the Java StampedLock abstraction, which is the main focus of the reader writer lock discussion we'll have today. So what is a stamped lock? It's basically a reader's writer implementation that came in Java 8. Before that point, between Java 5 and Java 8, there was something that was called the reentrant read-write lock, which we'll see later is deficient. So stamped lock was added by my good buddy Doug Lee as a way to overcome the limitations with the earlier version, which he had also implemented as well, but discovered it was not appropriate. And its main benefit is it's much more efficient and scalable, and it's got some cool features that are not in the legacy classic reentrant read-write lock abstraction. So basically, we have a stamped lock class, and this doesn't implement the read-write lock interface. There's a read-write lock interface that's defined in Java 5. That is not used by stamped lock, and nor does it use the abstract queued synchronizer, which is used by lots of the other synchronizers in Java, like reentrant lock and condition object and semaphore and so on, and reentrant read-write lock. And it also does not apply the bridge pattern. So it's really stripped down in terms of its implementation leanness, and so it's much more efficient. There are 3 types of locking modes, and many of these modes go way beyond what's available with the legacy reentrant read-write lock. There's writing mode, and writing mode is a pessimistic mode. And what that means is when you use write mode, you're expecting there to be contention, and so you're going to just acquire the lock in write mode. And as you'll see, what that means is that you're actually going to block, if necessary, until you can have exclusive access to that lock, to that stamped lock. So I always think about, writing mode is the glass is half empty, right? Because it's pessimistic. It's not half full. All methods here, which we'll look at in a second, write lock, try write lock, etc., all return something called a stamp value. And that's why they're stamped locks. And a stamp value, which is just implemented as a long, contains a couple of pieces of information which are sort of ORed together using bitwise operations so that you can put multiple pieces of state into one efficient token, which is the long. So it contains the version number, which is kind of the timestamp. Think of it as a timestamp. It's a monotonically increasing value. It's not really the timestamp, but it monotonically increases. So it basically expresses an epoch. It captures an epoch in time. And it also contains a mode that indicates what mode it's in, read mode, write mode, etc. The write lock method, which you'll get a chance to use, acquires a lock exclusively, meaning there's only one thread that can own this thing at a time. And it'll block the caller thread if necessary to get that lock. Now, of course, if there's no contention, it just gets it. But if there's somebody else who's already got the write lock, then it's going to have to block. Likewise, if there are other threads who have the read lock, write lock will also block because it has to wait for them to clear out before it can get exclusive access. There's another method called try write lock, and you'll have to, no, I take it back. You won't have to know how to do this one, but you'll do something similar to that. Try write lock will attempt to acquire the lock exclusively, and if it's available, it'll get it. But if it's not available, it will return with an indication that says, sorry, Charlie, I couldn't get that exclusive mode lock. It just wasn't available at this point. So try again later. And then there's also a timed variant of try write lock. So if you say, wait up to 2 seconds to get the right lock and then return with failure if you can't do it, that's what try write lock does. So that's writing, right? The goal is to get exclusive access. Reading, in contrast, is trying to get non-exclusive access. You can have multiple threads that acquire the locks in reading mode. And so there are 3 methods. Once again, they're somewhat similar. We have read lock, which will try to acquire the lock non-exclusively. So what that implies is multiple threads could simultaneously return from read lock, and they'd all keep going because they all have read locks, or they all have the read lock. And that will block, however, if someone else is owning the write lock. So if someone already has the lock for writing in writing mode, then read lock will block until that's released. Conversely, if someone else has acquired the lock in read mode, read lock will return right away. It'll get it because it's non-exclusive. There's also a try read lock, which tries to get it, and if fails, if it can't. And then there's a time version of that. So those are reading and writing. Those are pretty straightforward. They actually make a lot of sense. That's not too dissimilar to what was available in the reentrant read-write lock legacy interface. Here's where things get really interesting. And this is what's called optimistic reading. So, if writing was pessimistic, glass half empty, right? Optimistic reading is glass is half full. And I always thought this was a rather clever imagery for half full, right? The glass half full. So what this essentially says is we're going to use optimistic read locks if we suspect there won't be contention, so that you can actually, so you expect that nobody else is trying to write to the lock. However, if somebody does write to the lock, there's a way to find out. And that's where things get a little subtle, and I'll explain how that works. So you can think about this as basically a probabilistic lock that is assuming we don't have contention, and when there is no contention, it's ridiculously cheap. If there is contention, however, we have to do some kind of protocol to fall back and deal with the fact that there was potentially contention. So here are the 2 methods that are important. Try optimistic read and validate. And as we'll see here, we typically use optimistic reads for fields, and we're going to store the values of the fields in local variables. And I'll talk about why we put them in local variables in a second. The main reason is that they're not contended, so you can have a read-only copy of something. And then we'll use those local variables for validation after we're done with our critical section. That probably made no sense whatsoever, so I'll explain it better in here. So try optimistic read is the main method that you first call. And what that does is that returns what's called an observation stamp. So it's a stamp like the other locks take, except it's going to be used for validation shortly thereafter. And what happens is that optimistic read does a volatile read on a field inside of a stamped lock, and that ensures that we're always getting the latest version of the field. So you don't have to worry about memory contention and memory visibility issues when using stamped lock. However, this volatile read is very, very, very cheap, so it doesn't have much overhead at all. All right, so assuming we've done try optimistic read, we get back this observation stamp. We're then going to go ahead and copy those values from the fields into local state, into local variables. And when we're done with our critical section, we're then going to call this second method that's part of the abstraction called validate. And what validate does is you pass it the observation stamp that you got back from try optimistic read. And if nobody has come along in the meantime and acquired a write lock for this object, remember this object is the thing we're protecting with the stamped lock. If the stamped lock has not been acquired in write mode, then we're like, whew, we lucked out. Nobody could have changed this thing, assuming they follow the protocol, of course. So assuming they're following the protocol, nobody has made any changes. So the values that we just read with an optimistic read lock are still valid. And so we'll just use them. Conversely, if a write lock was acquired in between the point where we did the optimistic read and we validate, if something changed, if a write lock was acquired, then something may have changed, and we can't trust the values that we read because they may have been modified in the meantime. And so then we're going to have to fall back and do some other stuff, and we'll talk about what that other stuff is in a second. The synchronization overhead of stamped lock for optimistic read, when there's no contention, in other words, when there were no write locks acquired, is really, really low. So if validate returns true, then we paid almost no cost whatsoever for doing an optimistic read. So in situations where the access patterns to the state you're trying to protect with a stamped lock are such that you very rarely have read-write contention, optimistic locks are ridiculously efficient. Now, as you'll see, if you do have contention, and you always have to be prepared for contention, then it gets more complicated. We've also got a couple of other methods that get used here in interesting ways that conditionally perform conversion across these locking modes, right? So remember, we've got read mode and write mode, and then we have this optimistic read mode. And so these methods here, which I'll start with the word try to convert, try to convert, these things convert from one mode to another. So, for example, try to convert to write lock, which you'll actually have to use for your assignment. That will conditionally convert a lock that's not a write lock to a write lock. Or I guess you could try to convert a write lock to a write lock, which will trivially succeed, but that would be kind of silly. So what happens here is if the lock state matches the stamp, in other words, here's what's happening. If we try to convert something to a write lock, then if it is a write lock, we're done, right? Because we're converting write to write, so that's trivial. If it represents a read lock, in contrast, so if you have the lock in read mode, as you will for your assignment 3B, then what it'll do is if the write lock is available, in other words, if nobody else is holding it, it will atomically release the read lock and return a stamp that indicates you have the write lock now. So you atomically and very efficiently upgrade the lock from read lock to write lock. That's what it means to upgrade, go from read to write. Yes, Amanda? Oh, it just makes sure that you're not doing this in some other random stamp that has nothing to do with what you're doing. So remember, the stamp keeps, yeah, it's just a sanity check. So likewise, if the stamp represents a read, an optimistic read, then if there's a write lock, if the write lock can be acquired, then return it if it's available. Otherwise, if you can't upgrade this thing from a read lock, either optimistic or non-optimistic read lock, pessimistic read lock, to a write lock, if you can't do that, then it returns 0, saying, sorry, Charlie, somebody else has already got this thing in write mode, you fail. And then we'll talk later about how you adapt to that or how you follow on to this and compensate for it. There's also a way to try to convert something to a read lock, and what that does is if it's currently a write lock, it will go ahead and atomically release it and obtain a read lock. That's what's called lock downgrading. So you go from having a write lock, which is the most powerful form of locking because it's exclusive, we downgrade it to a read lock. You might do that if you needed to have a write lock at the beginning to make a change, and then after that point, you're done, so other people could go ahead and access it for reading if you needed to. If it's already a read lock, you're done. If it's an optimistic read, try to upgrade it to a regular read, a pessimistic read. Otherwise, fail. And then the last one is try to convert to optimistic read, which is kind of a wacky thing. So basically, it will let's see, if the stamp represents holding a lock, so in other words, if the lock is held, release it and return an observation stamp. So that's really downgrading. That's super duper downgrading it. And if it's already an optimistic read, we're done. Otherwise, we fail. I've never used convert to optimistic read. That's probably kind of crazy, but it's there for completeness. Okay, given the fact that we have all these different modes that a lock can be in, we need to think about how we release the lock when we're done with it. And it really comes down to, do you know concretely and definitively if this thing is a certain kind of lock? If so, use the release method that corresponds to that. And if you don't know, use the release method that will figure it out on its own. So if you know you have a write lock and you need to release it, use unlock write. You'll use that for your release method in the Palantir manager that you write. Unlock read does the same thing. If you know you have a read lock, it'll go ahead and release the read lock. If you're not really sure what kind of lock you've got at this point, and you'll see in a second why you might not be sure, then use unlock. And unlock will go and figure it out what kind it is, and it'll unlock it. And the reason why you want to try to use one of the other two if you know the type of lock is because unlock is a little bit less efficient because it has to check internally to see what kind of lock it is and then call either unlock write or unlock read. Whereas these guys don't have to do that because you call them directly. Now, the question that you should have at your top of your mind in the moment is, how the heck would you not know what kind of lock you've got? And the reason is because you may end up trying to do these upgrades or downgrades, and depending on whether they succeed or fail, your locks may have changed mode. And so by the time you go to do a release later, you may not know what kind of lock it is. So then in that case, you just use unlock because it's keeping track of that behind the scenes. Okay, so that's the end of part 2.